Yesterday we talked about power functions. Today we're going to talk about polynomial functions. And this is going on page 45 when we're done. Okay. So here is the definition of a polynomial. A polynomial is a function of this form. And I know that looks crazy and weird, but a polynomial could have an infinite amount of terms. Maybe it only has, 3 or more, or 2 or more, but it still could have an infinite amount. And so since we would define it for all of them, n could be, well, it could be 5 million, it could be 50, it could be 2, who knows. But if we have a sub n, this right here is the coefficient, which is a number, times x to the n power, then this is a sub n minus 1 times x to the n minus 1 power, and then n minus 2, x to the n minus 2, dot, 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 because we don't really know how many are in between because we don't know where we started, and all the way down to x squared, x to the first, and then x to the 0 power. Not sure why these 3 dots are there. This shouldn't be there. But I could have x to the 50th power plus 4x to the 49th power and keep on going down and have all those terms. I could have x to the 37th power plus 4 times x to the 10th power plus 7, and just have 3 terms and had started there, because some of those, it is possible for some of these coefficients to basically be 0 and them just not even be there. But the coefficients here, a sub n, all these, I know these things make you feel weird and push you out of your comfort zone, but it's not really this bad when we get into it. But the coefficients, or the numbers in front of our variables, are real numbers. Okay? And a sub n cannot equal 0, because if this first coefficient equals 0, then that zeroes out this whole term and we don't actually start with x to the n. So it's kind of a no-brainer. I don't think you would be confused about that and think it would be 0 or anything like that. And this is important too, n is a positive integer. That means no negative exponents. So not only do I have no negative exponents, since they're integers, they're also not, I don't have any rational exponents. So no fractions in my exponents, no negative numbers, just nice, pretty whole number, positive whole numbers for exponents. Okay, so shape and continuity. Shape is important here. Polynomials are smooth curves with no breaks and are continuous for all real numbers. Okay, so smooth curves, that's important. Everything is curvy in here. We don't have, nothing comes to a sharp point when you're graphing. Everything is curvy, and there's no breaks, so I don't have any discontinuities, which means it's going to be continuous for all real numbers. Okay, we need to make sure we understand what the degree of the polynomial means. Okay, so the highest exponent, which is n, is called the degree. And polynomials are classified by degree. So the highest exponent n is called the degree. Polynomials are classified by degree. So it's important here that you understand that it is the highest exponent, not necessarily the first exponent. If you actually have it written with an exponent order from greatest to least like it should be, then it would be the first. But it is possible that you get something that's mixed up, so make sure you don't fall into that trap and you actually look at the highest one. Okay? So let's look at these examples. We have these functions, and we're going to have to figure out what the degrees are and classify them. So I want you to think about this one right here. What do you think the degree of that one is? The answer I get there a lot is 1. Okay, well, if the degree of that is 1, then what would the degree of this one be? Well, you're thinking 1 or you're thinking 2, but remember the degree is the highest exponent. So let's start here. The highest exponent you have is 2. So the degree of this one is 2. The exponent here is 1, so the degree is 1. here this doesn't even have an x, but if I forced that on there, if I do f of x is equal to 2 times x, what would my exponent have to be here? It's not 1 because that would give me 2x. The exponent here would be 0, and anything to the 0 power is what? It's 1. It's not 0, so it's 1. So this is equal to 2 times 1, and that's where you get the 2 from, right? So we wouldn't write it like this. We just write the 2, but this is what's happening and why that works. So our degree here then is 0. This is a first degree. This is a second degree. Then the highest exponent is 3. So on all the rest of these, the first term does have the highest exponent, but remember they could possibly be mixed up. So this is 3, this is 4, this is 5. So if we're going to classify it, if I just have f of x equals a number, then that is a constant function. If my x is to the first power, this one is linear. Squared. Think about what that word is. For some reason we still struggle with that word, even though you've heard it a bazillion times. That would be quadratic. A third degree polynomial is called a cubic. We talked about fourth degree and fifth degree yesterday, so think about that or look at your notes. Think about fourth degree, that one was quartic. And then fifth degree was quintic. And then you could have hexic and heptic and octic and so forth and so on. Okay, so those are some examples of our degrees. We're going to talk once again about end behavior. We have talked about end behavior a lot, almost every single day for a while, and we've written it out a lot. So since we keep doing that, do you think it's important? The answer to that is yes. That's why we keep doing it over and over again, because we got to make sure that we got this down, because this is what's going to really help us with our sketching when we get to that. So my end behavior here, it says the power and coefficient of the leading term, okay, and that would be the highest one, determine the end behavior of the function. So the power and the coefficient. Now, this is almost identical to what we wrote out yesterday, but yes, we're still going to do it because I'm going to add a part to that. So same thing here. We're just looking at end behavior. We have an even power, positive coefficient. This is what we're thinking in our minds. So we would write out as x approaches infinity, f of x approaches infinity. And then as x approaches negative infinity, f of x approaches infinity. So for the other three, I want you to go ahead and get them written out, but don't flip your paper over because I'm going to come back and add some stuff on here. As I write them, I'm not going to talk you through it because I want you to write them down on your own. You don't need me saying it. You don't even need to look up here, but I'll complete it too so we can talk about it. But I'm going to write in silence so that you can write it down without me talking you through it. Fill these three in and then wait for me to continue with you. Okay, so hopefully I've given you enough time to write all that out. So let's talk about what I'm going to add / kind of change here. Now, yesterday, what we filled in looked, again, almost identical to this. It might have been identical. And yesterday, these pictures made sense because we were just talking about power functions. And if you have an even-powered positive coefficient and it's a power function, meaning it's a monomial, so whether it's x squared, x to the 6th, x to the 5,000th, whatever, then it should still have this exact same shape. But now we're talking about polynomials. And once you add in extra terms in there, the shape itself is not always going to look like a parabola, and it won't always look like a cubic if it's odd. So I feel like these pictures are kind of misleading. Remember, the idea here, we're talking about end behavior. We don't care about the middle stuff. I don't care about what's going on in here. This isn't always going to be accurate. And that was one of the things that was a little confusing to you about end behavior early on, was you were trying to focus on stuff that was in the middle because you didn't understand why we weren't looking at that. Remember, it's end behavior. Don't care about middle behavior right now. So since they're not all going to look the same, then I could, because I could have this. Let's say that I have an even-numbered polynomial function with a positive coefficient. It could look something like, instead of looking like a parabola, it could look something like this. Okay, that's a possibility, right? Or it could look something like this. Okay, which would mean it would be negative because it's pointing down. Because remember, it's the end behavior that's consistent, not the middle behavior. So what the picture I want you to have in your mind, and I'm going to make you sketch down instead of writing this sometimes. So that's a good thing. You won't have to write this out every single time ever when we do end behavior. Right now, yes, we're still doing that. We still have to get the idea of a limit down. But if I have an even-powered positive coefficient, and I know as x approaches infinity, f of x approaches infinity, and as it goes negative infinity, it approaches infinity, the end behavior looks like this. Because literally, I only care about the ends right now. The middle, I figured that out with something else. But it's the end. That's what the end behavior looks like. And if the degree of the polynomial is even, then the end behavior is the same. It's either up, up, or it's down, down. So it's up, up if it's an even power and it's positive. If it's an even power and negative, then the end behavior looks like this. So although I wouldn't expect you to be able to tell me much about these graphs right now, you still should be able to tell me this graph right here is an even-powered polynomial with a positive coefficient, and this would be an even number with a negative coefficient. So then odd power positive coefficient, remember it's end behavior that's consistent, so it would look like this. It's like the end behavior of a cubic. So you can still think about the cubic in your mind, but remember, you only care about the end stuff. The middle stuff could be different. And then odd power negative coefficient, remember all that negative does is reflect it in the x-axis. So it looks like this. Okay? So here's the other way to remember it. Even, they're the same, right? Up, up, down, down. Odd is opposite. So odd is opposite. That shouldn't be that big of a deal because so it's either up, down, or down, up. But when it's positive, the up is on the positive side of the x-axis. When this is negative, the positive or the up is in the negative part of the x-axis. So maybe that could help you remember. So if I draw a couple of other things, let's see. I will draw this and this. So I want you to think about this. When you look at these two, you can get these drawn too, so you kind of have an idea of what to look at here. When these two functions here, they're clearly both going to be odd polynomials because the end behavior is opposite. And then you just have to decide after that if it's positive or negative. Well, remember that the positive one is up on the positive side, and the negative one is up on the negative side. So this would have a negative coefficient that's odd, a negative coefficient odd degree. This would have a positive coefficient odd degree. So we know something, even though I don't expect you to give me the equation or anything else at this point. Okay, so the little pink things I have sketched here, that's what you need to start having in your mind for end behavior. And you know what? If you can get this sketched, then you can get this written out pretty easily because you see positive infinity, negative infinity, negative infinity. They go together. Okay. So let's do a couple of those on the other side. When my board decides to cooperate and catch up. It's thinking about it. All right. So on the back, it says, using the leading term, give the end behavior of each polynomial function. So what I actually want you to do, and do a couple little extra things here, is I want you to tell me the degree. So the degree here is 4, right? So if it's a 4th degree polynomial, then this is what's called a quartic. Okay. And then, so it's an even number, it's an even degree because it's 4, and it's negative. So if it's even, the end behavior is the same. It's either up, up, or down, down. So since it's negative, it is down, down. So my end behavior looks like this. Okay. So I got the name of it, I got the end behavior written. After I have that, then I can actually write out my little sentences, which we won't always have to write out every single time, but that is part of what we're doing today. So instead of looking at this and trying to figure it out, I know what this looks like. So I can say, as x approaches infinity, f of x approaches, well, as my x gets bigger, my y's get smaller, so that would be negative infinity. And then as x approaches negative infinity, f of x approaches, again, negative infinity. Okay? All right, so here's what we're going to do on 2, 3, and 4. All I want you to do on 2, 3, and 4 right this second is to write down the names of them, okay? Whether it's quartic, quadratic, whatever. So for 2, 3, and 4, look at the highest degree and write down the name like we have here. Like this one is quartic. So write down what 2, 3, and 4 are without looking up here, and then we'll talk about them. Okay, so let's see if we agree on the names. 2 has a power of 5, so it is a quintic, right? Like quintuplets, which is a scary thought, but that would be 5. And 3 is 6x squared, so that is quadratic. And quadratic. Get that word down, because some of y'all still struggle with that. I don't know why. Then number 4, it is a 7th degree, so it's heptic or septic. Either one, remember, either one is acceptable. Heptic or septic, it would be fine. I don't care. All right, so now we're going to go back, and on 2, 3, and 4, all I want you to do is what I have in pink here, and draw in the little end behaviors. Think about whether the degree is even or odd, and positive or negative, and what you think the end behavior looks like. Try and do it without just copying down what I'm doing, and then we'll talk through it. All right, so that's what I have for my end behavior. See if you agree. Let's talk about how we're supposed to know that. So this is an odd exponent, which means they're opposite. So it's either up, down, or down, up. And then this is negative, right, which means there's a reflection. So it's up on the negative side of the x-axis, down over here. Or it's like a reflection of the end behavior of a cubic. This is a quadratic, so it's even and it's positive. So when they're even, they're the same, and it's positive, so it's up, up. This is odd, which means they're opposite, and it's positive, so it's down, up, or up on the positive side of the x-axis here. Now that we have that, that tells us what our end behavior is and what we need to do to write these sentences. So I want you to write those out for 2, 3, and 4 without me talking you through it. So do it without looking up here. All right, so see if you agree with me. Now I want you to think about the even, that they're the same, and odd is opposite. It's true for this part here too. This is even. So even is the same. So if this is negative infinity, that's negative infinity. Odd is opposite. So if this one's negative infinity, this one has to be positive infinity. Even, they're the same. Infinity, infinity. Odd, they're opposite. Infinity, negative infinity. Okay, and you can get that from your little pink picture there. Right. So hopefully we're good on end behavior, but those little pink graphs are like a really important part right now, so that we know literally just the ends. Don't care about what else is happening. All right, so we're going to skip 5 and 6. Let's look at numbers 7 and 8. It says describe both the power and coefficient of the leading term of the polynomial given the shape of the graph. I do not expect you at this point to be able to give me the equation. You don't know how to do that yet. That's fine. I don't expect you to necessarily give me the degree with a lot of confidence, but you can tell me some things. You can tell me the degree, whether it's even or odd, and you can tell me if the coefficient is positive or negative. So when we look at number 7, since the end behavior, the ends are opposite, I know that it has to be an odd power. Okay? Or an odd degree, is what I'm really meant to say. Which is still an odd power, but it's odd power on the first term, or on the highest term, and this will erase in a minute. Okay. But it's an odd degree polynomial is what I meant to do. Okay, so I know it's odd, and then I have to decide if that coefficient is positive or negative, right? So my cubic, which is where I get my end behavior, looks like this, right? So if it's going this way with my end behavior, then that means there's been a reflection, so we have a negative coefficient. So now look at number 8. See what you think about number 8. See if you can figure out what the degree is and what the coefficient is. I'll give you a second for that. All right, so let's see what we think about degree. The ends are the same. So since they're the same, it needs to be even. So it's an even degree. Even's either up, up, or down, down, right? And since this is up, up, like a parent function of a parabola, that would mean that we have a positive coefficient. Okay, so that's all I expect you to be able to tell me at this point. We'll get to the rest a little bit later. Okay. So let's talk about turning points. So turning points, it's the points at which the polynomial function switches direction. So I'm going to show you on number 7 real quick, because we've talked about these already. We're just kind of talking about them again in a different context. But my function here is decreasing. It gets to here, and then, oh, it's increasing. And then it gets to here, and it's decreasing. Then it gets to here, and it's increasing. Then it gets to here, and it's decreasing, right? So each one of these points is a turning point. Just like here, these are my turning points, because I'm increasing, I get to here, now I'm decreasing, now I'm increasing again. So those turning points have names. We've already talked about them. Okay, it is where they switch direction, right? If your turning point is higher, like this one, than any nearby point, it doesn't say higher than any point altogether, because this is not the highest point, because this goes off to infinity. But it's higher than any point around it, then it is a maximum value. It's not the absolute maximum. It would be the relative maximum. Then if the turning point is lower than any nearby point, it would be called a relative minimum. So we've already talked about minimum and maximum. And minimum and maximum values are called blank. They live in this little category of stuff. Think about what that might be. One of the things that I'm told a lot here is critical points, and they are critical points. However, we can be a little bit more specific than that because critical points also includes points of inflection. But these are extreme values, so they are called extrema. That is plural for that. They're called extrema. So turning points define where the function is increasing or decreasing, where it switches from one to the other. Now, to actually find them, there's a calculator part on here, which we're not doing, but I left it on here because I wanted to talk about it. Because there's a lot of stuff that we can find, but there's also some stuff that we can't find algebraically yet. Like the actual maximum and minimum values to find all of those, that requires calculus. You're not in calculus, you're in pre-calculus. So using pre-calculus skills, maximum and minimum values, we cannot find all of them, and that's okay. We're going to find what we can find. Could we use the calculator to find them? Yeah, but you know what? Here's how you do it. You either push some buttons and bam, it just magically gives you the answer and you have no idea why or concept of what the heck's going on. Or you can trace your little spider and take a wild guess at it, and that might get us a more decent graph, but that doesn't really tell us how to find maximum and minimum. But algebraically, we don't have those skills yet. So what we're going to do is we're going to algebraically find what we can find. And when we get to graphing, we're really going to be more sketching because we're not going to have exact maximum and minimum values, which is fine. So I left it on here. We're not filling it out. We're not going to do it like ever, but I just wanted to let you know that's kind of the only way you can do it now without some calculus skills. And we don't need them. That's not what we're doing. So we're going to focus on what we can do. All right? So that is it. You can go ahead and glue this in so that you are not waiting until the last minute right before a test to do that and then get a bad ISN grade. And then when you get your assignment, you need to work. You can either work on what is due tomorrow or work on this, but you need to work and be nice to Miss Williams. And I will see you tomorrow.